Hello everyone. Today I wanted to document Knuth-Morris-Pratt algorithm, and I wanted to revisit this because I just came across another like intuitively very tough to understand algorithm called Corsic. Some of you must have heard of it. So this was one of the uh, I guess like at least to understand how or why that algorithm works. So I revisited this, and again, this KMP algorithm is not a very like intuitive algorithm. Like if you, it's very tough to come up with it in a short time if you don't know about it. And yeah, so I just wanted to document this for my future understanding. I don't have to go through all of this again and uh, like waste a day or two understanding it. So here's my attempt at it. The question is very simple. Find the index of the first occurrence in a string, right? So you're given a haystack, you're given a text, and you're given a pattern. So you have to return the first index where it occurs. And if it does not anywhere in the string, you just return -1. So the problem statement is pretty simple. And the quadratic time complexity algorithm to do this is very simple. You can maybe use just like the index of function in Java to find this, but this is a quadratic time complexity, and there's a better way to do this in linear time. Yeah, so let's go about it. So again, uh, there's a text given, right? Suppose and there's a pattern given. Now you're supposed to find the first occurrence of this pattern in the text. So the answer in this case would be 0, right? Because from index 0, you can just match these strings and you have the answer, right? The brute force way or the quadratic way to do this would be, so suppose I have a string MD and pattern is AYMD. So I would start from here. So I'll try to match these characters first, right? So whenever they don't match, I increase the I value to 1 and start matching it again. So in the worst case, this is the pattern and this is the text. In the worst case, I would have something like this, right? So I would match these, they all match, but at the end, these two don't. So I'd move the pattern string down and match these characters. They don't match, these ma don't match, so I'll move the pattern string one step to the right and match it. So it's very easy to find out the time complexity in this. It is of quadratic. So for like the pattern, for each character, for each index in text, you're trying to match all the characters in the pattern one by one, starting from index 0. So this is quadratic time complexity. Now, how does Knuth-Morris-Pratt or KMP get over this problem? Well, how does it uh, like get rid of rematching the characters which were already matched in the previous iteration? So for this, you need to understand another concept called longest proper prefix. That's also a suffix. So what does this mean? So you have a string A, B. Okay, so this is your string. So if you take just this string, this character in the string, first of all, to clarify, what does a proper prefix mean? So for this string, A, empty string, A, and A are all prefixes. But proper prefix is are all the prefixes, uh, n- all the prefixes except the entire string. So the proper prefix for ADA would be AD, an empty string, but not ADA, because that's the entire string on its own. So this is not a proper prefix. Longest proper prefix, that's also a suffix for each length. So this is a prerequisite for KMP. So building this array, we'll get to how to build it, but building this LPS array is a prerequisite to KMP. Now, for the first string, for the first character, for the string is A, right? So we need to see what are the proper prefixes first of all. It's empty string. That's it, right? Because A is the string itself, so it's not a proper prefix. So uh, the proper prefix, which is also a suffix in this case, is of length 0. Now, for the second index, let's take this string, AA. So, proper prefixes are A and empty string, right? But this proper prefix we can see is also the suffix A. So, this A equal to this A, right? So, in this case, it'd be 1. Now, for the third index, we take this string, AAA. So, proper prefixes are A, empty string, AA, right? This AA is the longest proper prefix, which is also a suffix. So the answer here would be 2. Similarly, for this case, it's 3. Now going to B, you have this string, right? In this case, what is the length of a proper longest proper prefix, which is also a suffix? So the proper prefixes are A, triple A, and 4 A's. None of these are suffixes of this string, right? So you can clearly see this string ends at B, but none of the proper prefixes end in B. So the answer here is 0 again. Similarly, for this case, it's 1 because A and A will match, nothing else. For this case, it's 2 now. For this case, it's 3, right? So this is our LPS array. So now you know the theoretical part of it, like what LPS array is. So how would you construct it uh, via code, right? So now you need to see some things. In the first case, you have a string, and suppose at this place the length was like we constructed LPS array here. So this is another some LPS array where we have processed these number of characters, and we are going to process something at I, which is here, right? So the suppose the LPS of this I minus 1 was let's say X, right? Now what can you say about LPS of I? You've calculated everything till LPS of I minus 1. So how would you go about finding LPS of I? There are multiple cases in this. For example, this was the length uh, at I minus 1. The LPS I minus 1 was len. So now you're trying to calculate LPS of I. This is I. So first thing to check here would be, uh, so if this first part was, this LPS of I minus 1 was len, that means some string, some string of length len is a suffix of my string from 0 to I minus 1. And these, the prefix of length len is equal to the string here, right? That is what LPS would suggest. So if LPS of I minus 1 was len, that means the first part, the first length len was similar to uh, length len at the suffix. That is what LPS is, right? LPS of I would tell you longest proper prefix. So this part, which is also a suffix, which is also a suffix. So this part of length len. So first thing you need to check is, and if this is length len, so this index right next to it is the index len because it's a zero index array. So it starts from 0 to len minus 1 till here, and this index is len. So if we know these two strings are equal, this first prefix of len, length len, and suffix of length len are equal, that means first we can check if str of I equal to str of LPS I minus 1, which is nothing but len. So what we're doing in this case is we're comparing these two characters. What we're trying to do is expand our LPS in case these two characters are similar. So in the case they are, you know this part equals this part. So this part of the string is similar to this part, is the same as this part of the string. And the ending character on the prefix side, if it is equal to ending character on the suffix side, that means we can increase our window or increase our LPS here. So if these two are, we have just increased the size of LPS at I by 1. So now LPS in this scenario, LPS of I is nothing but len plus 1. This is easy to understand, right? So there's no problem here. But now in the second case, what if it's not? So this condition does not hold. What happens here? So when you try to match this part and this part, they did not match. So clearly you can't expand our LPS because this part of the string is not same as this part of the string now because the end characters are different in both of them. So what do we do? Do we just write it as LPS of I as 0 or 1? Not really. I'll give you an example. So now I have a string AXD MMM SP and something in between AXD triple M and AXD, right? So you encountered a character I here. So this is what we are processing. This is the LPS we're processing now, right now for this index. Okay. And you had J over here. So this is the case where ending of the prefix does not match the ending of the suffix. So these two don't match. So what is a better way of like calculating LPS here? Do we start from the beginning again and try to find the longest common the LPS at this index? No. What we can do is think about this. So this string you can say is C is similar to this string, right? So first of all, this part was equal to this part. That is why we tried to expand our LPS window from this length to len plus 1. In case they were equal, we would have done that, but they're not. So now what we do, the LPS of this index tells you what which is the longest suffix ending at this index, which is also a proper prefix, right? So we can see the value here would be 3 because AXD match AXD here, right? Now we just need to apply something very logical here. So this part of the string was equal to this part of the string. Similarly, because they were equal string, this part of the string is equal to this part of the string, right? And we know because this is the LPS, this here is the LPS, this is equal to this part of the substring. And this is equal to this. So technically, by the transitive property, this part of the string is equal to this part of the string. Just because this was equal to this, and this again was equal to this. So this part of the string is equal to this part of the string. So what we can do is when we get to the point where the ending characters don't match, we can reduce length to be LPS of len minus 1. So how would this work? So first, we try to the length was LPS of I minus 1, right? Which gave you this part. So this is length, right? Now, when they did not match, what we try to do is then go to recursively call the LPS of this part. And this works because the transitive property of this. So this part of the string is equal to this part of the string because LPS is just that. So what is the suffix that is also a proper prefix? Long is suffix, right? And we know the whole string, this whole string was equal to this whole string. So the ending part of this string was equal to this part of the string. That's why this part is equal to this part of the string, right? So when we do this, we first have len equal to LPS of I minus 1. We already discussed this here, right? Now, we saw that stri does not match something at str len. So these two characters did not match. So what we do is just reduce length to then be LPS of len minus 1. So we now start taking smaller substrings from the prefix and try to get to a point where some part of it matches the ending part of the suffix that we are trying to calculate. So you keep recursively doing this until you find the string. So now in this case, first you had len equal to this. So let me just calculate the indexes of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So we had len equal to 9. Now, because we got LPS of len minus 1, so LPS of 8 equal to 3. Now my len is 3. So it's here, right? Now I'm gonna try to match these two characters. If they match, I'll just increase it from whatever the length was here. So it was 3. If they had matched, I would just increase it to, and if this was also M, if this was also M, I would say these two match. So my new LPS of I is 3 plus 1. So this is the idea behind finding LPS array. It's a little tough to get your head around it in the first go, but this is the prerequisite. So let me just try to code this out. Okay, so what I'm gonna do, so let's say M was his stack length, N was needle length. And important thing to remember, we create the LPS array on the pattern, not the text. So this would be of length N, or the pattern length. And I'm just gonna call a function to fill my LPS, right? What do I need to pass it? LPS, N, and also the pattern. Yeah. So now what we're gonna do? So for the initial character, LPS will always be zero, right? Because for string of length one, the only proper prefix will be an empty string. So LPS zero is always zero, but in Java that'll be taken care of because it with default initialization of an array, the values are always zero. So this would be zero anyway. If not, if you're using some other programming language, you need to like initialize it to zero, which does not have a default. Now, secondly, I'm gonna have a right variable, right pointer, which is gonna try to keep track of the current position. So I'm trying to fill out LPS of I. So basically, I'm gonna have I start from zero and len is again zero, right? Because uh, right now the LPS is of length zero, so this is our length. Now, while I is less than n, what I'm gonna do is for the first case. So in the first case, the character at I equals the character at the previous LPS value. So if you remember, we said we first need to check if str I equal to str of LPS I minus 1, right? This is what we're checking. And this is the case where we're trying to expand our LPS in case the characters match. So if they do match, we'll have LPS of I equal to len plus 1. Len would then become LPS of I, and I would increment I. So, for example, uh, the string was A till now. So we're processing the last A, right? So in this case, when we entered the loop, len was 0, right? Because LPS of 0 was 0. Now we reach this case where we're trying to expand the window. So we're trying to see if this is equal to the end of previous LPS. So end of previous LPS was at 0. So we're seeing if A equal to A. It is. So LPS of I. LPS of 1 would then become 0 plus 1, 1. And length would now be 1. And we would increment I to process subsequent string, right? This is the simple case. Now, for the second case, for else value. So they do not match. In this case, again, there are two cases. So first simpler case is that your len becomes 0. So your len was 0. That means nothing matched for the previous LPS values. So in this case, you would just simply write LPS of I equal to 0 and I plus plus. So think of a case like this, B. Okay, so you're at this index. So the previous value, in this case, the previous value was what? 3, right? So till this string, what is the LPS ending at the last A? It's 3, right? Because you can match the first 3 characters, which is the proper prefix, longest proper prefix, with this suffix. So you match 3. So len was 3. Now you try to match this character, the current character at I, with index 3. So last A. It did not match. So it got changed to, as we discuss, we'll keep recursively checking. We'll keep reducing length as LPS of len minus 1, right? So in this case, we checked it was not equal to B. So we checked at len minus 1. So at this index, what was the LPS? It was 2. So we checked A and B again, did not match. So this way, our len reduced to 0 when we came to the first index, right? So in this case, we did not find any matching characters. So we just defined LPS of I as 0 and move the pointer. else len changes to LPS of. So this is our entire filling out LPS part. We can check it for the time being. I'll just return some random value and I'm just gonna. So let me see. This should all give 0. This should give 0 for everything again. Yeah. I'll try to get a case where I don't get 0. Okay, sorry. So I'll give this, right? So the LPS array in this example should be 0, 1, 2, 3, 4, 5. So let me run this. Okay, let me see what the problem is. Oh, 1 second. We should start from 1. Oh, give me a second. Let me check what the issue is. Okay, my bad. Since our pattern is a string, not a integer value. Okay, so for this third case, we're getting the proper LPS array. So we filled out LPS. Now let's go back to how KMP is gonna use this LPS array to get an answer. Okay, so now we have an LPS array. Now go back to our example that we use. So suppose it's B, 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 C, B. Okay, this was our text, and our pattern was B, 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 A, B, B. Okay, this was the pattern. So going back to our brute force solution, what were we gonna do? We're gonna match these characters. They match properly. Now, when we came to this part, okay, let me just shorten the pattern length. When we came to this part, they did not match. So in the brute force, what did we do? They did not match. So in the brute force case, we matched these characters now. They did not match, so we didn't incremented I, and then from starting of I and starting of j, we match the characters j from j equal to 0, right? Now, just think about how LPS could help in this case. So we see that, 1 second, here. So in this character, there was a mismatch. So now instead of again starting from j equal to 0 and matching it with I equal to 1 to whatever the ending, I'm going to use LPS in this case. How is that possible? So we know this part of the string match this part of the string, right? Only the end characters did not match. So what I can do now is use the fact that this part of the string was equal to this part of the string, right? And the LPS value at this point would have said, in this case, it would have said 3, right? Because longest prefix, proper prefix, which is also a suffix, is this BBB. So of length 3. So I know that these two matched, these three characters match with these three characters. and LPS here was 3. So I know this string was equal to this string, right? Just try to wrap this, to get this whole idea what we're doing here. So in the brute force, we would have just moved it, we would have moved the J pointer, which is iterating through the pattern, to 0, and then incremented I by 1 because there was a pattern mismatch at this place. We would have moved I equal to 1, and then from here, we would have started matching to the rest of the string with resetting the J pointer to 0, right, at the beginning. But now we are bringing LPS into our picture. How that is helping us is we knew this part of the string matched this part. More specifically, this part of the string matched this part, right? And we know LPS at this index was 3. So this part of the string is equal to this part of the string. So again, using the transitive property, these two are equal. So this part of the string is equal to this part of the string. Now see what happened here. Instead of again resetting J to 0 and then matching each character again, we already know these three match with these three. So we can just match this to this part and we can move forward. So this is how KMP helps us in reducing the number of matches that we're doing between character. So we're using LPS to find out how far back we have to move J pointer. So we're not moving the J pointer back to 0 again. We're only moving it to a place where we haven't matched certain characters. So in this case, we knew BBB, this BBB, match this BBB. So we don't need to match them again. We'll just start with J equal to 3, right? Now, this again, the crux of KMP works very similarly to LPS. So we start off by while I less than n, right? If let's call it text of I matches pattern of J. So remember J is moving along in the pattern and I is moving along in the text. So if they match, we just increment both the pointers and move forward, right? Now, else case is a little tricky, very similar to LPS, but still a little tricky. And let's assume we'll fill this else case later. So we're just going to check if J equal to N. So basically, N was the length of the pattern. So if J moved completely to the end, right, we can just return I minus J at this point. So this means that we were able to match all the characters in the pattern to somewhere some substring in the text, right? Now this case again uh, is very similar to uh, our LPS algorithm. So what we're gonna do in this case is we're just gonna reduce J to LPS of J minus 1. So in this case, so let me write this again, B. So we found a mismatch here. Our J was this place, right? And our I was this place, right? And there was a mismatch. So instead of now moving I to 1 and I to 1 here and J back to 0 and then matching all these characters, what I'm gonna do is I'm just gonna move J to uh, LPS of J minus 1 character. So what this will tell me is, in this case, LPS of J minus 1 was 3, right? So I'll move my J index to 3. So J will be here and I will be here again. And we'll try to match it, right? Because now we know 0, 1, 2 indexes of pattern were already matched with this part of text. So this is very similar. So if j equal to 0, uh, what we're gonna do? We're just gonna increment I plus plus again. So we have to, like, if there was no matching proper prefix, which is also a suffix, j would end up here, right? And then we gotta start matching each again and increase I, LPS of j minus 1. So this is the complete algorithm. So now we have the LPS array. What we're gonna do is have another pointer starting at, let's just call it I equal to 0 and then j equal to 0. So both start at the, j starts at the starting of the pattern, I starts at the starting of the text, which is the haystack. Okay. So while I less than n, our first part is to check if haystack is needle character at j. We increment I and increment j, right? Else, if j equal to 0, so we did not find any prefixes which were also the suffixes. So we just increment I and move on and start comparing I and j again. Else, I'm gonna reduce j to LPS of j minus 1 to avoid matching characters which were already matched in the previous iteration, right? Okay, there are a few problems here. So I traverses the haystack, not the needle. So M. And finally, if uh, J has reached the end, like all the characters in the pattern were matched, we're just gonna return I minus J, wherever the I was uh, minus J, right? So that will be the starting of the first match. In case nothing gets returned from the while loop, you'll have minus 1 returned here. This seems to be working. Yeah, so it works. So this was an easy question, but if you see the constraints, they're not huge. So you can have a quadratic solution and you can just use inbuilt functions to do that. But if this were increased to something where quadratic does not work, you'd have to have a linear time solution. And KMP is the way to go about it. Yeah. So thank you.